This is the third screencast for Chapter 7, and we're going to start off looking at metallic character. So if you want the nice, pure, easy answer for this, we can simply say as we move from the right side of the table towards the left side of the table, metallic character is going to increase. And we probably are pretty familiar with this already. We know that the nonmetals are sitting over on this side of the staircase, and then everything to the left of that staircase are the metals, with the exception, of course, of hydrogen, which is a nonmetal. And then we also see that the metallic character increases moving down the table. And really the only place that kind of comes into play is when we look at the P block. We know that this is a lot of nonmetals. We just mentioned that. And we're on this side of the staircase, the right side. Those are considered to be the nonmetals. And then, of course, you have on the zigzag line, the ones that are in purple, those are listed as the metalloids. But then you get these ones down here, for example, aluminum, gallium, moving on down. You notice that these are considered what are called other metals. Not the best name, but that's what they're called. So we notice as we move from top to bottom, the metallic character of these groups tends to increase. So, for example, you have tin and lead, which are over here in the P block, and they are considered metals, even though they're in the carbon family. So, okay, so there we go. So just something you want to try to be aware of. Now, as far as some general guidelines, you learned these all last year, so I won't spend a whole lot of time. I will go over these in just a little bit as far as what metal oxides do and non-metal oxides do in the next slide, or a couple slides down the road. As far as charges go, you're fairly familiar with this. Ones in group 1 are considered to be a +1 charge. If you're in group 2, it's a +2 charge. And then if you're in group 13, you're a +3. Group 4, we tend to skip. Never mind these guys down here. Then you get over to group 15, and now we're on the other side of things where we're gaining electrons, and then it just tends to go down over here. And then, of course, group 18 doesn't do anything. They have a full octet of electrons. They're not very reactive. But these guys in the middle, these transition metals, what we tend to see is when they're losing electrons, they're not losing it from the D block. So, for example, scandium, it loses 1 electron. That's, okay, fine. That one is probably coming from the D block, that 1D electron. But titanium, the electrons that it is losing are going to be its S block electrons. Vanadium, notice it's losing 4. What it's most likely doing is losing 2 of its S block electrons and 2 of its D block electrons. And of course, if it's losing 5, it's losing, well, all of those exterior electrons. And you can see how these trends kind of play out moving down the table. If you look at copper, let's see, it's losing 1 or 2. Remember, copper was kind of one of those weird ones where it had a full set of D electrons. By pulling one of its S block electrons into its D sublevel, so when it loses 1 electron, it's losing that remaining S sublevel electron. If it's losing 2, it's losing, well, the one it has sitting over here in the D block, and 1 over in the S, or both, however we want to take them away. It's losing 2 electrons total. And zinc is just losing those 2 S block electrons. Okay, you can look at that quite a bit on your own. Just some of the characteristics of metals. Again, this is kind of a repeat what was on that other slide. You've learned this before, so I won't spend any time on this. The one thing interesting as far as when metals are mixed with water, and a nice easy example is to look at sodium. If I mix sodium oxide, we want the oxides. If I mix sodium metal with some water, what you're going to get, and this is a molecular form, we won't, or ionic actually, we won't break it apart, is you tend to get sodium hydroxide. And there's 2 of those, so I don't know if my balancing is here correct or not. If I put this in here, that gives me 4. It looks like it's going to be a mess. But in any case, you're going to get some sodium hydroxide. So they tend to form bases when you put them in metal or put them in water. And after you mix that with water, they tend to dissolve. So metal oxides tend to dissolve in water. And if they don't dissolve in water, you can put them in with a stronger acid and they'll still dissolve. So usually if they get it to dissolve in water, in acid, you're looking more so at a transition metal. The group 1s and 2s typically will either dissolve in water or they'll dissolve in like steam. So those are the metal oxides. So metal oxides typically form basic solutions. So something to remember there. Now, nonmetals are pretty much just the opposites. And again, you learned these last year. If shinies are metal, shinies are metals. If metals are shiny, nonmetals are dull. And you can just kind of go back and forth with the different characteristics of those. So going back to if metal oxides form bases, got to remember that, then non-metal oxides typically form acids. And a nice easy one to remember with that is sulfur trioxide. If I mix that with some water, this one I think I can just rip off here, we're going to end up with H2SO4. So that one's pretty easy to do. So H2SO4, sulfuric acid, that's going to separate, of course, in water, and you're going to have an acidic solution. So non-metal oxides plus water form acidic solutions. Metal oxides form basic solutions. Got it. Metalloids are those ones kind of on that zigzag line. There's typically 7 that are listed, and they're kind of in that no man's land area. They have some metallistic characteristics, and they have some non-metal characteristics. And they kind of vary depending which element you have me talking about. So, some trends. Looking at some of these, the alkali metals, sodium, lithium, potassium on down the line. Those are typically soft metals, and they always show the example of cutting it with a knife. They tend to lose electrons more readily, and again, this is just based on reactions, not necessarily what we were talking about as endothermic or exothermic. None of them lose them exo or endothermically. They all have energy required to remove an electron. So they all require energy. I said endothermic. It is an endothermic process to remove an electron from any metal. Okay. Looking at the trends, one of the things you'll notice on here is the boiling point, or excuse me, the melting point, decreases going on down there. And this is based on the metallic character of these things. As they become further apart from each other, the atom grows larger in size, there's less of an attraction between them. And this is based on metallic character. So when you can take a look at the trends, how they generally increase in one direction going down. Looking at group 2, keep moving along here. Looking at group 2, we can see that trend continuing. As we go down the group, we can see that the melting point is going to decrease. And again, just because the atoms are further apart from each other. And this has a lot to do with metallic character of them, the thing that attracts one atom to another. And you can see how the other trends kind of stay the same with it. Then, moving over to group 6, which is the oxygen group, notice it's slightly different here. Polonium, I can never really get what's going on with that one. It's a little bit of an oddball. But notice the boiling point tends to increase moving down the group. And this has a lot to do with no longer being metallic character, even though we do have that going on because they have higher melting points. They are more like metals. But it has more to do with the type of attraction these have for each other. It's not so much as metallic bonding any longer. It's more about these van der Waals forces, which we'll talk about in the next chapter. And this trend will continue later on the next one. One thing I wanted to mention here really quick is an allotrope, which is how some atoms kind of find themselves attracted. For example, oxygen has 2 main allotropes. You got regular oxygen, and then you have ozone. Sulfur can find itself as an allotrope, but it has 8 atoms, so 8 sulfur atoms in a grouping, just to mention. All right, group 17, or group 7 in this case. Same idea that you have the melting point is or melting point is increasing, going down the group. And this has, again, one, they're diatomic, and it has to do with the type of forces, which are going to be van der Waals forces, London dispersion forces, that are attracting them more so as they get more electrons in them. Next chapter, I think, chapter 8. Halogens, the properties of these things you've learned before as far as how they react and what they react with. Noble gases, same idea in regards to the boiling point or melting point increasing, going down the line. Okay, I think that's pretty close to it. And it is. That's the last lecture for Chapter 7.